Hello everybody. Welcome to lecture 24, which is on L'Hopital's rule. So we're going to begin by taking a look at a particular limit. So we're going to look at the limit as x goes to 0 of e to the x minus 1 over sine x. And the first thing you try naively is you're just going to take this number 0 and try plugging it in and seeing what happens. So if you plug in 0 for x, it turns out that you get 0 over 0. And we know from lecture 8 that this is an indeterminate form. So usually what we would do is we would do some kind of algebra to fix the problem, and then we would plug in 0 after we're done. The problem is we haven't encountered any algebra techniques so far that allows us to do that with this. So we need some other tool, and that's where L'Hopital's rule comes in. So I guess I'll just write a summary of what happens here. So right now, we don't have an algebra or algebraic technique to handle this. So to handle this limit. So that's the idea. So we're going to have L'Hopital's rule to come to the rescue here. So let me write the statement of L'Hopital's rule. So this is L'Hopital's rule. And here is the complete statement. So suppose you have two functions, f of x and g of x, and they're differentiable. So they are differentiable. And g of x does not equal 0 near x equals a, except possibly at x equals a itself. So this just has to be true near some value of a, but not necessarily at a. We saw a similar idea with the squeeze theorem when we did that in exam 1. So suppose that this is true. So here it is. So if either the limit as x goes to a of f of x is 0 and the limit as x goes to a of g of x is 0. So if either this thing happens, I'll call it 1. So both of those things have to happen at once. That's why I put an and. Or you could have this second thing happen. Or the limit as x goes to a of f of x equals plus or minus infinity, and the limit as x goes to a of g of x is plus or minus infinity, then, so if one of these two things is true, either this one's true or the second one's true, then you get the following conclusion. Then, to do the limit of f of x divided by g of x, what you can do is just do the limit as x goes to a of the derivative of each function and just take that ratio instead. And I also want to point out, while I'm here, is that the one-sided limits are also the same too. So it doesn't just have to be the general limit. You also have that this is true for the one-sided limit. So I'll just write as x goes from a on the right side, but you could also have or from the left side as well. So this rule also works for one-sided limits. I just want to point that out. OK, so here's the rule. A lot of words, but through many examples, we will get an understanding of what this means. So the example I want to go back to is actually this thing right here, because this is a nice first example. So let's go back to the limit as x goes to 0 of e to the x minus 1 over sine x. So this one right here is f of x, the e to the x minus 1. That's f of x in this situation. This one here, that's g of x, the denominator. Notice that we're in situation 1. Both of them went to 0. And I wrote it right here. It goes to 0 over 0. That's the indeterminate form. So because where in this situation, both of them went to 0, I can use L'Hopital's rule. So here's how you do it. Anytime I use L'Hopital's rule in this class, I'll write this cursive L above an equal sign, and that's how you know what I did. So this is equal to the limit. My a this time is 0. That's the a we're talking about here. So still 0. But now what you do is you take the derivative of each piece separately. You do f prime, and you do g prime separately. This is not the quotient rule. I should even write this over here. Do not, do not do the quotient rule. We are not going to do low d high, high d low here. You just take the derivative of each piece separately. It's a much easier problem than doing the quotient rule. So what is the derivative of the numerator separately? Well, it's going to be e to the x. What's the derivative of the denominator separately? It's cosine of x. And now we try again. So if you plug in 0, you're going to get 1 over 1, which is 1. So because this one is 1, it means the original problem, this is also equal to 1. So that's L'Hopital's rule. So it's really important. So important. Check the indeterminate form before using L'Hopital's rule. There's only 2 different indeterminate forms that you're allowed to directly use it on, and it's these two, 0 over 0, and you could see a plus or minus infinity over infinity. It's these two that I've stated right here. If you don't see one of these 2 forms, you're going to have to do something first to turn it into these 2, or you can't use L'Hopital's rule at all. Okay, so this is really important that you check ahead of time to make sure you can use the rule. Let's look at another example. So this next example is going to be the limit as x goes to infinity of ln of x over x squared. So if I suspect I can use L'Hopital's rule, I'm going to check the form of the indeterminate, and it needs to be one of these 2. So if you plug in an extremely large number, so as x tends to infinity for this, ln goes to infinity, and x squared, if I plug in a huge number for x squared, that's also going to go to infinity. So I get infinity over infinity. That's good for L'Hopital's rule. That means we can proceed. So this is equal to the limit as x goes to infinity. And then here I have the derivative of the numerator. We learned that is 1 over x over the derivative of the denominator is 2x. And if you simplify this, what I can do is I can take this x and push this into the denominator. So I get 1 over 2x squared. And we have to ask ourselves, do we know what that new limit is going to be? And we do. We have a constant over a very large number. So 1 over something tending to infinity, that's 0. That's from exam 1. So that means that the original limit is actually 0 as well. Okay? So again, we checked first, and then we applied it. Notice that x doesn't have to just go to a finite number. Over here, I can say a can be plus or minus infinity as well. So you don't have to just go to a finite number like I did here with 0. A can also be positive or minus infinity. Okay? So keep that in mind. Let's take a look at something you might not use L'Hopital's rule for. So this is I'm going to call it a non-example. Here you have the limit as x goes to pi of tangent of x over x. So let's say I just was like, I had tunnel vision on the exam. I'm like, oh, that's got to be L'Hopital's rule. I haven't seen one yet. You just immediately did it. So let's pretend. So this is us pretending. OK? I'm going to use L'Hopital's rule. The derivative of the numerator of tangent is secant squared. And then the derivative of the denominator is 1. So if I go ahead and plug this in, I get secant squared of pi. Well, secant of pi is going to be 1, and then I square it and I get 1. So we get 1 over 1. However, that's not what the answer is. So if you go back over here, so let me say that this is wrong. Aggressively wrong, just caps. Here, if you just try to plug in pi, like if you had checked first, if you plug in pi, tangent of pi is 0. And you get over pi. 0 over a number besides 0 is just 0. So the actual limit is supposed to be 0, and you would have got it if you just plugged it in and checked first to make sure you could use L'Hopital's rule. 0 over pi is not one of these two indeterminate forms. It's not 0 over 0, and it's not infinity over infinity. So you should always check first to make sure you're good. This is not wrong. This is what they'd be trying to do to trick you on the exam, to get you to use it when you're not supposed to, okay? So always check first. All right, we've done a few examples. I'm going to come back soon and give you even more complicated examples of this rule. So I'll see you soon. All right, welcome back. So for the remainder of the video, we're going to be practicing L'Hopital's rule with different examples. So what's key in this section goes back to lecture 8. These are the 7 indeterminate forms that we learned for exam 1. So I've listed them here. So if you see any of these, this could be an indication that you need to do L'Hopital's rule. These are the first 2 that you can actually use L'Hopital's rule directly. So use L'Hopital. If you see any of these other 5 indeterminate forms, we're going to have to do some algebraic manipulation first to turn it into one of the first 2, because these are the only 2 indeterminate forms you can use L'Hopital's rule for. I will repeat that over and over and over again until you're clear on that. I'll say it more than I need to, just so you always check before you use L'Hopital's rule. So what am I going to do first here is I'm not going to do the problem. I'm going to check and see if I can use L'Hopital's rule. So if you plug in 0, because that's what a is here, if you plug in 0, you get 1 minus 0 is 0 over. If you plug in 0 down here, you get 0. So this is all set. This is an indeterminate form, and not only is it an indeterminate form, it's the first one. So you can use L'Hopital's rule directly. So this is equal to the limit as x goes to 0. And you take the derivative of each, the numerator and denominator, separately. So derivative of the numerator is e to the x minus 1. This 1 just goes away, and this becomes minus 1 over 2x. That's the derivative of the denominator separately. Now you try plugging in 0 again and see if it worked. You plug in 0, you get 1 minus 1 is 0 over 0. That's not a terrible thing. It's an indeterminate form, but the good news is that you can just use L'Hopital's rule again. So sometimes you need to use it more than once. So sometimes you need more than one application of L'Hopital, the rule. That's OK. As long as you keep getting the indeterminate form, keep checking at every stage, you can keep using it. So let's go again. So this is equal to the limit as x goes to 0. The derivative of the numerator this time is going to be e to the x. This time, this 1 disappears. And the derivative of the denominator is 2. Now we can plug this in, and it's a real number. If you plug in 0, you get 1 over 2. So that means that the previous limit was 1/2, and also the one before that was also 1/2. They're all 1/2. All right, so this one is equal to 1/2. Let's look at this one. So first thing you should always do is check. We're going to plug in 0. You get 1 minus e to the 0 is 1, so we get 0 over. Secant of 0 is the same thing as 1 over cosine of 0. Cosine of 0 is 1. We get 0 over 1. So actually, I put these quotation marks because I'm writing something that's usually not a real number. So I'm putting like quotes, like it's, you know, it's this. However, I can erase these for this one. Because what is 0 divided by 1? That's a real number. It's not an indeterminate form. It's 0. So no L'Hopital needed, because when I checked, that directly computes to 0. OK? So that's sometimes you're rewarded for checking ahead of time. You finish the problem. Let's look at this one. So I'm going to rewrite this just slightly. I'm going to say this is the limit as x goes to 0, 1 over x minus cosecant. It's reciprocal. It's the reciprocal identity of 1 over sine. I'm going to write it like that. So what's going on here, I'm going to plug in 0 to find out. So if you plug in 0, 1 over 0. So 1 over a denominator that's approaching 0. This is some form of infinity. And so is this. 1 over another 0 here, sine of 0 is 0. You're going to get something here that looks like infinity minus infinity, which is an indeterminate form. This is not 0. You cannot just say that this is 0. So if you look over here, this is the last one on my list. So we're not stuck. We just have to take this and try to turn it into one of these two forms right here. What's very common with fractions is all you have to do is get a common denominator, and then you sort of get what you need. So let's get a common denominator. So I'm still not using any rule, L'Hopital's rule yet. We're just transforming this. So what is my common denominator between x and sine x? It's just putting them together. So multiply the first one by sine x. Multiply the second one by x. Basically, multiply each fraction by what it's missing. You're going to get sine x minus x over the common denominator, which is x sine x. So that's just some algebra to combine that into one fraction. Let's take a look at where we're at now. Plug in 0. You get 0 minus 0 is 0. Over 0 times 0 is 0. That's good news. So we've taken this, we transformed it, and now we have it looking like that indeterminate form, which is one of the two that you can use L'Hopital's rule for. So we're going to go ahead and do it. Now it's OK to use L'Hopital's rule. Derivative of the numerator separately is cosine minus 1. The denominator is probably the most complicated derivative we've had so far with these. This is the product rule, right? That's from exam 2. So the product rule would say that this is 1 sine x plus, leave the first one alone, x cosine x. All right, so now we cross our fingers. We hope that that helped. So you plug in 0 into this. And we're going to get 1 minus 1 is 0 over. Plug in 0 to this. You get 0 plus 0 is 0. OK, that's not the end of the world. It just means the problem isn't over. But we get 0 over 0, which means you can use L'Hopital's rule again. So start from here, and let's go again. So this is our second application. We have the limit as x goes to 0. Derivative of cosine is negative sine. Derivative of sine is cosine plus the derivative of x cosine x is another product rule. So it'll be 1 cosine of x, and then plus, leave x alone, and then minus sine x. So I'm going to take a step back just to make sure I've got that correctly. I kind of spaced out for a second. Sorry. Cosine. It looks like we're good. Now we plug in 0 and hope for the best. The numerator is 0. OK, hopefully we get a number on the bottom that's not 0. Cosine of 0 is 1. So we get 1 plus, here's another 1, plus 0. This is 0 over 2, which that is a real number. 0 over 2 is not an indeterminate form. So the limit is 0, which means all the previous limits are 0. So the answer is 0 for that one. So again, this one was an indeterminate form. We turned it into an indeterminate form we can actually work with. All right, let's try this one. So this very last one, I have 1 minus 2x to the 1 over x. I should probably give you a limit to work with here. So this is the limit as x goes to 0. Sorry about that. I just didn't write the complete problem. Limit as x goes to 0 of this. Well, let's see what we're dealing with. We could get lucky here. And this might not have to be done. But you can see I left all this space here. So I'm probably going to use this space, right? So you can guess it's not going to work. If you plug in 0, you get 1 in the parentheses. 1 over 0, again, is some kind of infinity. 1 to any other real number power is 1. However, look at my list over here. The fourth one on my list is 1 to the infinity. That's an indeterminate form. Not only that, it's not one of the first two, so we can't use L'Hopital's rule right now. However, we learned about other techniques to deal with stuff where we have a variable expression to a variable power. So let me show you the way that I learned in high school and was so stubborn I never stopped using this way. So let me show you my way. So the way I do this is I say let y equal the limit as x goes to 0, 1 minus 2x to the 1 over x. So I let y equal the thing I'm looking for. To get a power down from here, you can use log. We did that in lecture 17 a lot. So take the log of both sides. Log of this equals the limit as x goes to 0, log of this. It turns out, with the type of function that we have, you can move log through the limit. Basically, they commute here, so that's OK. So I'm going to do that. So you have log of this expression right here. This is equal to the limit as x goes to 0. I did that on purpose now so I can bring the 1 over x in front. So you get 1 over x times log of 1 minus 2x. However, this right here, instead of multiplying by 1 over x, just make x the denominator. So it's the limit as x goes to 0, log of 1 minus 2x over x. That's the same thing, right? You just have it on the denominator. At this stage, I see a fraction. I'm going to try plugging in 0 and see if I have the right type of indeterminate form. So if you plug in 0, log of 1 is going to be 0. That's true for any log. If you plug in 0 to it, or 1 into it, you get 0. Plug in x, or plug in 0 for x here, you get 0. This is good. So now I've turned it into 0 over 0. It was 1 to the infinity. A very common way to deal with that is you use this log technique, and you can turn it into 0 over 0, which is now ready to use L'Hopital's rule for. So this limit, by L'Hopital's rule, is equal to the limit as x goes to 0. What's the derivative of the numerator separately? Well, for log, it's 1 over whatever is in here. 1 over this, 1 over 1 minus 2x, times the derivative of the inside by the chain rule. So the derivative of the inside in here is negative 2. That was the derivative of just the numerator. Derivative of the denominator is much easier. So derivative of x is just 1. I hope at this stage we can plug in 0 now, and we don't get another indeterminate form. If we do, and if it's 0 over 0 or infinity over infinity, we would just do another L'Hopital's rule. But I think we're good here, because if you plug in 0 for x, there's only one spot to do it. You get negative 2 over 1. This would be 1 down here. So the answer to this is negative 2. OK, but that's not the final answer. So you have to think a little bit about what I did. So if you follow my equalities, go left, go all the way back up. The very first part of my inequality, ln of y equals all this, equals, you just follow the equal train, equals negative 2. So let's join them together. ln of y equals negative 2. That's what I just showed using all these. How do you solve for y? Go back to the prereq stuff. To cancel ln, you take e on both sides. So base e. Y is e to the negative 2. Remember, that's what I wanted all along. In the very beginning, I'm like, OK, this is the problem. I'm going to say y equals the answer to the problem. And here it is. Here's y. Y is the limit I was looking for. So that's my answer right there. All right, this is honestly just the start. There's lots of examples of L'Hopital's rules. You should go practice your Cronus problems, practice previous exam questions. You should be comfortable with all different types of L'Hopital's rules that can come up and experiment with all these other different indeterminate forms you get, and then how you fix them and use L'Hopital's rule. Do problems where you have multiple applications of L'Hopital's rule. There's lots to practice with this. And until next time, I'll see you in lecture 25. Have a nice day.